Dear children, myself Mathew, faculty in physics at Classes School. Welcome to the lecture module on wave optics. Let me start with the term optics. Optics is the branch of physics which deals with the study of the fundamental properties of light and its interaction with matter. It includes classical optics and quantum optics. Classical optics includes ray optics and wave optics. Ray optics is also known as geometrical optics and wave optics also known as the physical optics. And in geometrical optics or ray optics, we consider light as a particle and it travels as straight lines. While in physical optics or wave optics, we consider light as a wave. So a material has both particle nature and wave nature that discussed in the quantum optics. So in wave optics, we are familiar with the phenomena reflections and refractions. It can be explained by using ray optics. We are considering light travels as straight lines or red linear propagation of light is considered. But certain phenomena like diffraction, interference, polarization, etc. cannot be explained on the basis of ray optics. It can be explained while considering light as a wave, or wave optics is used for explain interference and diffractions. This lecture module includes first Hygen's principle, then reflection and refraction of plane waves using Hygen's principle, interference, superposition principle is the basics of interference, then Young's interference experiment, then comes diffraction, diffraction due to a single slit, then resolving power of telescope, then finally polarization, polarization by reflection and Rossier's angle. Before going to discuss about wave optics, let me discuss something about the milestones behind, historical milestones behind the development of wave optics. In 1621, Snell's proved Snell's law. Snell's law, that is sine of angle of incidence to the sine of angle of refraction, is equal to the refractive index of that medium. But it's an empirical relation. There is no theoretical proof behind that formula. So in 1637, Descartes gave an explanation for this Snell's law. But after Newton modified that theory, and after that it is known as Newton's corpuscular model of light. Then in 1678, Huygens first put forward the wave theory of light. But he couldn't explain certain aspects or certain properties of wave. So the corpuscular theory or Newton's theory still prevailed. Then after 100 years, in 1801, Young's interference experiment takes place. And from this experiment, it's proved that light is a wave. Then after 1864, Maxwell's theory of electromagnetic waves comes. After that, light is considered as an electromagnetic wave and that travels in a direction which is perpendicular to electric field and magnetic field. Then comes the introduction to waves. What is a wave? In our daily life, we encounter many types of waves. The sound waves, the light waves, the radio waves, the microwaves, etc. Then what is a wave? Wave is a periodic disturbances or variations that transfer from one place to another. Or we can represent a wave as oscillations accompanied with transfer of energy. So it's an oscillations. We can use the equation of simple harmonic wave for representing a wave. So this is the expression for simple harmonic wave. y of x comma t equal to a sin kx minus omega t, where this term y of x comma t represents the disturbances and this term a represents the amplitude of that wave. Then the k, the term represents the propagation vector or propagation constant, which is equal to 2 pi by lambda, where lambda is the wavelength of light. Then about omega, which is the angular frequency of that wave. And this is the wave that is propagating in the positive x direction. So these are the terms. Then there are the different properties of this wave or characteristics of this wave. The properties are the amplitude, the wavelength, the frequency, the period and the linear velocity. Look through a figure. In this figure, this is a wave and this is the rest position. This is positive displacement and this is the negative displacement. This is maximum positive displacement. This is again the maximum positive displacement. These points are known as the crest of the wave, and these points the maximum of negative displacement. These B and D, these points are known as the trough of the wave. And a wavelength can be the distance between two consecutive crests or two consecutive troughs. And amplitude is the distance between the rest position to the maximum position or the rest position to this maximum position. It is the amplitude. It represents how much energy the wave carries. And about period is the time for which the wave travels for a fixed amount of time. And frequency is the number of cycles at a given instant of time. Then last, the linear velocity, which is the velocity by which the wave travels, and velocity equal to frequency into wavelength. V is equal to f into lambda, where f is the frequency and lambda is the wavelength of the light. Then coming to wavefront. Wavefront we can explain by a simple example. When a stone is thrown in a calm pool of water, then we observe a pattern like this. A photograph is taken, then it would show circular rings that would propagate with maximum amplitude or maximum displacement. It shows concentric circles of the waves of maximum displacement, which means that, consider this circle, the particles on these circles are vibrating in the same phase because the particles on this circle are at equal distance from the center or the source of disturbances, so that the particles are vibrating in the same phase. For considering every other circular rings, the same pattern, all the particles on that ring vibrating in the same phase. So we can define a wavefront as the locus of all the points that is vibrating on the same phase is known as the wavefront. So this is the first wavefront, this is second, third and so on. And the shape of the wavefront depends upon the source of disturbances. Depending upon the source, the shape of the wavefront varies. There are three types of wavefronts. According to the source of disturbances, there are three types of wavefronts. One is spherical wavefront, and then cylindrical wavefront, and last plane wavefront. Depending upon the source, whether the source is a point source, then we will get a spherical wavefront. This is the example for a spherical wavefront. This is a point source and this represents the part of the spherical wavefronts. First wavefront, second wavefront, etc. And the ray of light which is perpendicular to the wavefronts. This arrow mark shows the wave or light ray and which is perpendicular to the wavefronts for a point source which create spherical wavefronts. And in the case of cylindrical wavefronts, it is produced by linear source. A linear source means the source which is a slit which is illuminated by lamp, then it acts as a linear source which produces cylindrical wavefront. And this is the example of cylindrical wavefront. The wavefront is in cylindrical in manner. And about plane wavefront, and the plane wavefront can be produced by these point sources or cylindrical sources or linear sources, but the sources are at infinity. They are placed at infinite distance, then the plane sources can be or plane wavefronts can be created. This is the case of plane wavefront. This is the plane wavefront and the light ray is perpendicular to the wavefront. These are the different cases of wavefronts: spherical wavefronts, cylindrical wavefronts and plane wavefronts. This is created by point sources, this is by linear sources, and this case whether spherical or the cylindrical wavefronts or point sources or linear sources which are at infinite distance or which is placed at infinity. Then comes Hygen's principle. Hygen's principle, in 1678, Hygen put forward the wave theory of light. Light travels as a wave. And by knowing Hygen's principle, we can able to find the position and the shape of the wavefront at a later time when we knowing the position and the shape of wavefront at a previous time. Okay. Then coming to Hygen's principle, the statement of Hygen's principle. The Hygen's principle states that every point on a given wavefront that act as a sources of secondary wavelets and which spread out the waves, secondary waves in all directions with the speed of light in that medium. And the new wavefront is the forward envelope or the tangent envelope of that secondary wavelets at that instant. We will come to this statement after a while. Consider a point source. We are considering a point source and the point source creating spherical wavefront. This is the case of spherical wavefront. Let F1, F2 represents a spherical wavefront. Then according to Hygen's principle, every point on this wavefront acts as sources of secondary wavelengths. And for convenience, we are taking some of the points. Let A, B, C, D, E are the points we are taking. And considering that the wave is moving with a velocity v, and we want to know the position of wavefront at the time t. This is the wavefront at time t equal to 0, and we want to know the wavefront at time t equal to t dash. Then every point on this wavefront act as sources of secondary wavelets according to Hygen's principle. Therefore, we draw circles of radii v into t, where v is the velocity in which that travels and t is the time. We know speed is equal to distance by time. For that, distance is equal to speed into time. Here velocity is v and time is t. Therefore, distance is v into t. Therefore, A, B, C, D are the points, and considering this A, B, C, D, E are centers with radii v into t and draw circles. We draw circles as A, B, C, D are centers and with radii v into t. So one circle is here, another is here, another is here, and similarly up to here. Then the tangent envelope of all these circles, gives the secondary wavefront at the time t is equal to t dash. So, if we know the wavefront at this time t equal to 0, we can able to find the wavefront at the time t is equal to t dash. And this is the case of point sources. Similarly, the source is at infinity, then we use plane wavefronts. Let F1, F2 be a plane wavefront. Every point on this act as point sources, it sends out secondary waves, and here also the radii is v into t. V is the velocity and t is the time. and the circles drawn, then the tangent of all these circles give the next wavefront or the secondary wavefront at time t is equal to t dash or time t is equal to tau. This is about Hygen's principle. And in Hygen's principle, in the later slides we consider only forward directed waves. But the back in this figure is showing this is the original wavefront and this is the secondary wavefront, forward secondary wavefront. This is the secondary backward wavefront, but we are not consider this wavefront because according to Kirchhoff, the intensity I is proportional to cos squared theta by 2. A wave that is propagating in a same direction as that of the wave direction, then theta equal to 0. Therefore, the term cos 0 equal to 1. Then intensity is proportional to cos squared theta by 2. Cos 0 equal to 1, cos squared 0 1. Then intensity is maximum. That means the forward direction intensity is maximum. While considering in the backward direction, in backward direction it's in a direction opposite to the propagation of the wave, so that theta is 180 degree, cos squared theta by 2, 180 by 2, 90 degree, cos squared 90, that is 0. That means intensity is 0. Intensity is 0 in the backward direction, and intensities and amplitude are related by intensity is proportional to amplitude squared. Intensity is 0, so that amplitude is 0. So the amplitude and intensity is neglected in the backward case. We are considered only forward case, so that the wave is moving forward. The forward wavefronts are obtained. Hygen's wave theory was able to explain the phenomena like reflection, refraction, interference and diffraction. But the phenomena like polarization cannot be explained by Hygen's principle, because Hygen assumed that the light wave is a longitudinal wave. But actually transverse can be explained in polarization. Then blackbody radiation, photoelectric effect and Compton effect also he can't explain. We will study this in the coming chapters. And we already discussed that in the ray optics we can able to explain reflection and refraction, but the wave optics is completely different from ray optics, and using wave optics we can able to define or explain reflection, refraction, then interference and diffraction. The first case is reflection and reflection of plane wave using Hygen's principle. In this case, look into the figure. A parallel beam of light that is incident on a reflecting surface. This black dot represents the parallel beam of light and this violet color represents the wavefront. These two are perpendicular. The parallel beam of light and the ray of light and the wavefronts are perpendicular, and which is incident on a reflecting surface. Then the point, consider this point as A, this point as B. Then consider the point A touches the surface at first, than the wavefront at B, so that the reflections takes place first in the case of A than the case of B. We will get reflected rays in this direction and reflected wavefront in this direction. If the incident wavefront making an angle I with the reflecting surface, then the reflected rays make an angle R with the reflecting surface. This will come in detail. So reflection of plane waves using Hygen's principle, and the reflection, when light is incident on the reflecting surface, it completely reflected into the same medium. So this is air, it is reflected back to air. This is the case. This is a ray of light. This 2 represents the ray of light which is incident on the reflecting surface. M and be the reflecting surface and AB be the plane wavefront. The parallel ray of light and the wavefront are perpendicular, so that AB be the plane wavefront and this is the parallel beam of light. And according to Hygen's principle, every point on this wavefront act as point sources which send out or spread out secondary wavelets in all directions with the velocity. And the wavefront A touches the surface first, so the reflected wavefronts emerges from the point A, and the time for which the wavefront from the point B advances to C, then the wavefront emerged from the point A covers a distance which is equal to BC. The distance BC, that is equal to V is the velocity in which it travels and T is the time, then the distance is V into T or velocity into time, V into T. Therefore, BC is equal to V into T. Then the reflected wavefront of this A covers a distance of V into T. And similarly, all the points act as secondary sources and it send out secondary wavelets. Similarly, similar wavefronts are obtained here. Then, if we draw the tangent of all that secondary wavefronts, we will get a reflected wavefront. So, CE represents a reflected wavefront. And the incident ray make an angle I with the normal, or we can say the plane wavefront, the incident plane wavefront make an angle I with the reflecting surface. Then we can suppose the reflected wavefront make an angle R. We have to prove this I equal to R because according to law of reflection, then we studied that the angle of incidence should be equal to angle of reflection, and also the incident ray, reflected ray and the normal all lie on the same plane. We have to prove the law of reflection here. So we suppose that this is R and we have to prove that this I equal to R. Then I already said this is the incident ray, this is the incident wavefront, this is the reflected wavefront. Reflected rays are in this direction. Then this is reflected ray and this angle, this is tangent and this is the reflected ray, and the wavefront and the reflected ray are perpendicular, which means this angle is 90 degree. Similarly, this is the incident plane wavefront and this is the incident ray. Again, this is 90 degree. Also, the distance BC equal to AE. The distance BC equal to AE. The secondary wavefront of A travels or covers at a distance equal to BC. BC is equal to V into T, then AE is again V into T. Then, if two triangles, their angles are equal, their sides are equal. Consider the triangles AEC and ABC. Consider the triangles AEC and ABC. Then the AC side is both common to both. Then AE equal to BC we already discussed. That means these two triangles are congruent. The two triangles are congruent means the angle opposite to the same side. The angle opposite to the same side means the angle opposite to the side AE equal to R and the angle opposite to the side BC equal to I, that must be equal. That means I equal to R. Angle of incidence I equal to angle of reflection R. That is, first law of reflection is proved here using Hygen's principle. And from the figure itself, the incident ray, reflected ray and normal all lie on the same plane which is perpendicular to the plane of the paper. This is about reflection of plane waves using Hygen's principle. Now we are going to see a refraction. Refraction means a beam of light coming to a refractive medium. It bends towards or it's bent away from the normal. That is the case of refraction. In refraction, we have to prove first law, Einstein's law, sine of angle of incidence to the sine of angle of refraction is equal to the refractive index of the medium. So here consider say plane wavefronts, only plane wavefronts are shown here, and this is the wavelength or distance, and it is incident on a refracting surfaces, so it bends and it's from rarer to denser medium because V1 is the velocity in the rarer medium and V2 is the velocity in the denser medium, and it shows that V1 is greater than V2. That means this is denser medium, this is rarer medium. In the denser medium, refractive index is more. By relation, in refractive index is equal to C by V, where V is the velocity. Then velocity, we know V is equal to F into lambda. Velocity and wavelength are directly proportional. That means the refractive index increases, then velocity decreases, again wavelength decreases. So the plane waves incident on this refracting surfaces, then Hygen's principle, as per Hygen's principle, secondary wavelengths are produced and the wavelength and the velocity of light in this medium decreases, and the pattern is shown like this. We will discuss more about this. This is the case, and a beam of light which is incident on a refracting surface, and V1 is the velocity of the rarer medium and V2 is the velocity of denser medium, and V2 is less than V1. That means it's denser medium and this is rarer medium. The parallel beam has a wavefront which is perpendicular in direction, that is AB. It make an angle I, the incident ray make an angle I with the normal, or we can say the wavefront make an angle, incident wavefront make an angle I with the refracting surface. Okay. Then similar case, the wavefront at the point, this is the wavefront, and according to Hygen's principle, every point on this wave acts as sources of secondary wavelets, and we are considering a point A. The point A touches the surface first, so secondary wavelets are produced, and similarly the secondary wavelets are produced in all these points, and the wavelets or wavefront produced from B take a time t to advance from B to C. That means it travels a distance v1 into t or v1 into tau, where v1 is the velocity in this medium and t is the time taken. The wavefront advances from B to C. At that time, the wavefront, the refracted wavefront of A covers at a distance v2 into tau. Here v2 means this is a denser medium, so velocity is less here. So v2 into t, it covers, the refracted wavefront covers a distance v2 into t or v2 into tau. Similar wavefronts are obtained here, and when the wavefront at the point B touches the point C, the wavefronts, secondary wavefronts observed here, and the envelope of all that wavefronts shows the refracted wavefronts. In this figure, CE represents the refracted wavefronts, and refracted rays are perpendicular to this refracted wavefront. And this is angle of refraction. This is coming from rarer to denser medium. So the bending of light, that is moving or bend towards the normal. So it bent towards the normal. This is angle of refraction R. So this is R, and this tangent, and this is the refracted ray and the refracted wavefront are perpendicular. That means this is 90 degree. Therefore, this angle is 90 minus r, therefore this is r, refracted angle r. And consider the triangles ABC, and from ABC sine of I, that is equal to opposite side by hypotenuse BC by AC. Then from this triangle AEC, then sine of R, that is equal to opposite side AE by BC. Then AE by AC, that is BC equal to, we know it's V1 into T and V1 into tau by AC. Similarly here AE equal to V2 into tau by AC. Then according to Snell's law, sin A by sin R, we are going to find whether it's matching Snell's law or not. Sin A by sin R, that equal to cancelling these terms, and we will get V1 by V2. V1 by V2. Then we are relating the refractive index and velocity. N is equal to C by V. Therefore, N1 equal to C by V1 and N2 equal to C by V2. Therefore, V1 by V2 as N2 by N1. Substituting this in equation number 1, sin A by sin R, that equal to V1 by V2, that equal to N2 by N1. From N is equal to C by V, or V is equal to F into lambda. So we can write V1 by V2 equal to lambda 1 by lambda 2. That means if a wave travels from rarer to denser medium, wavelength changes, its velocity changes, but frequency remains same. Its frequency remains same, but the wavelength and velocity changes. And from this equation, sin of I equal to sin of R, that is equal to the refractive index of the medium, N21 or N2 upon N1. This is Snell's law. So we proved Snell's law here. And the laws of refraction, first one is the Snell's law. So incident wavefront, that the refracted wavefront and the refracting surface all lie on the plane which is perpendicular to the plane of the paper. That is the second law of refraction. Then from Snell's law, sin of I by sin of R equal to N2 by N1, that equal to V1 by V2, that equal to lambda 1 by lambda 2. We already studied in the chapter of ray optics. And in the other case, later in the earlier case we discussed the ray travelling from rarer to denser medium. Consider the case the ray travelling from denser to rarer medium. What happens? In the denser medium, velocity is less, and the rarer medium, velocity is more. So the difference from that, the earlier diagram is that this is the velocity of light in the denser medium, and this is V1 tau, because V1 is the velocity of this denser medium. Then the ray travels to rarer medium, so the refracted ray moving away from the normal, making an angle R, and the time for which the wavefront reaches from V to C, at that time the wavefront, secondary wavefront at A covers a distance V2 into tau, where V2 is the velocity in this medium. The velocity is more in this medium, so that this length, compared to these two lengths, this AE is more than that of BC, because the velocity is more in this rarer case or in this medium. So V2 tau is greater than V1 tau. This is the case of the ray travelling from denser medium to rarer medium. Rest of the things are same as that of the earlier case. And one more case here. The case we discussed that the ray is travelling from denser medium to rarer medium. Then the sin of I to the sin of R, that is equal to the refractive index of the medium. Then if the case that the refracting angle is 90 degree, then we will call it as, that is critical. The incident angle is known as critical angle IC. Critical angle IC. Then the refracting angle is more than 90 degree, or which means the angle of incidence is greater than critical angle, then there is no more refraction, only total internal reflections takes place in that case. Please do the activity by drawing the behavior of wavefronts in reflection and refraction. That in the case of concave mirror, convex mirror, then refraction, concave lens, convex lens, and also for the prism. Remember, do all the activities before coming to the next session. Till then, bye.